Okay, in this video, we're going to put all of our techniques together, and we're going to use it to try to find all the zeros of a polynomial and to write it in factored form. So we're going to find all the zeros, write in factored form. And to do this without a calculator, I'm going to give you 1 0. So 1 0 has been provided to us. And after we do all this, we want to describe the end behavior using limits. So we're looking here at this first problem. We have a degree 5 polynomial. So I know by time it's all said and done, I got to have 5 roots. They could be complex roots, but I'm going to have 5 zeros of this thing. So I have 1. And what I'm going to do is I'm just going to kind of help myself organize this. I'm going to write I'm going to make a little column here for my zeros. And then I'll turn that into factors later. So I got a 0 of 3. And now I got to go hunt for all the other ones. Well, since I have a 0 of 3, what I can do is I start the process of division to get the other ones. So because 3 is considered a linear factor, like x minus 3, I can do synthetic division. I'm going to take all of my coefficients of f. So 1, negative 3, 6, negative 18, negative 27, and 81. And I'm going to do division, see what I get. Now, because I know that's a 0, I better end up with 0 as my last number for my remainder. And I do, so that's good. That means basically all we've done is we've confirmed that x equals 3 is a 0. And we need to write what's left after we did that division. What's left is x to the 4th. I have 0x to the 3rd. So I got plus 6x squared, 0x minus 27. And so this becomes our new problem. Well, I still have to find the remaining 4 zeros, and this is the stage we're at. We're going to try to see if hopefully we can factor this problem to see what's left. And so I need to know, where does this equal 0? And so through the process of factoring, so I'd have x squared times something with another x squared is equal to 0. Make negative 27, add up to 6, plus 9 minus 3. And so here we have our 2 problems to solve. So we'd have x squared plus 9 is equal to 0. And x squared minus 3 is equal to 0. And then we solve for x both times. So I'd have x squared is equal to 3. I take the square root of both sides. Remember, the square root of x squared is the absolute value of x, which is going to give us x is equal to positive or negative the square root of 3. So there are 2 more zeros. I'm going to go add them to the list before I forget about them. So I have positive or negative the square root of 3. So I have 3 out of my 5 accounted for. And my other 2 are going to come from x squared plus 9. So that gives me x squared is equal to negative 9. I take the square root of both sides. Square root of x squared makes the absolute value of x. The square root of negative 9, 3i. And so we have x is equal to positive or negative 3 times I. So there goes our other 2 zeros. So plus or minus 3i. So I have all of my zeros here, all 5 of them. Now graphically, you were only going to see 1. You were going to see the 0 at 3. And so to write this thing in factored form, what we're going to do in factored form, so the factored form, we're going to write this as x minus 3. So this first 0, x minus 3. And then instead of writing this as x minus 3i and x plus 3i, we're going to use the 2 factors that generated those that did not result in whole real numbers. So we'd say times x squared plus 9 times x squared minus 3. So there's my factored form. Now lastly, we wanted to find the end behavior, which means that we go back to our original problem. We look at the highest degree term. So I have x to the fifth, 1x to the fifth. So according to our leading term test, we have a positive coefficient and we're odd degree, which means that I know that left side goes down, right side goes up, and our end behavior, describing it using limits, would be the limit as x approaches negative infinity for this polynomial is going to equal negative infinity. And the limit as x approaches positive infinity for this polynomial is going to equal positive infinity. And let's do this process one more time. And we want to accomplish the same goal. So I'm given a polynomial, in this case degree 6, and I want to find all of my zeros. So I know that when it's all said and done, I have to have 6 zeros in my list. Well, I look at what they give me. They give me 1 0 to start with, so I know that I have 1 plus 4i as a 0. Now remember our rule, if you're given an irrational or a complex number root, the conjugate is also a 0. So I also have 1 minus 4i as a 0 as well. And so now we got to see, well, I got to go get 4 other zeros in this list. You can do synthetic division with a complex number. Me personally, I don't like doing it that way. So what I'm going to do is I'm going to reverse engineer the factor because I also have the goal of writing this thing in factored form. So I'm going to say x equals 1 plus or minus 4i. To reverse engineer the factor that created the 1 plus or minus 4i, you got to isolate the plus or the minus and then square everything. So that would be x minus 1 squared is equal to 4i squared. And that's going to be x squared minus 2x plus 1 is equal to negative 16. And so our factor is going to be what we have when we set that equal to 0. X squared minus 2x plus 17 is equal to 0. So there is a factor. So I have a factor, if I wanted to make another list here that coincide with my zeros, my factor for those two zeros would be x squared minus 2x plus 17. Now I got to figure out, well, all right, I did that part. Well, I got to get my other zeros. So what I'm going to do is I'm going to turn around and I'm going to do long division. Hooray. So I'm going to take that factor, x squared minus 2x plus 17, and I'm going to divide that into this long problem that we were working with. So I got to make x squared become x to the 6th. I do that by multiplying it by x to the 4th. That's going to give me x to the 6th minus 2x to the 4th, or excuse me, 2x to the 5th plus 17x to the 4th. We subtract. Zoom in here, make it a little easier for you to see. Then I need to make x to the 6th cancels. I'm going to have negative 3x to the 5th plus 4x to the 4th. Drop the next number down, minus 41x to the 3rd. And then do the process over again. So I want to make that x squared become negative 3x to the 5th. So I'd be timesing it by negative 3x to the 3rd. And then times it to all of my terms. Okay, so we did long division, and what we have to work with now is we have this polynomial x to the fourth minus 3x to the third minus 2x squared plus 6x that we want to solve for all the zeros. Now, notice, and I could have actually did this before I did the long division, is that everything has a factor of x. So I could factor out an x and write everything I got left. So it'd be x times x to the third minus 3x squared minus 2x plus 6 and equals 0. Now, that x tells me that I have a factor right here of x is equal to 0. So I'm going to write 0 as in my zeros list, and its factor here that I get, corresponding factor is x. I need to kind of like make a line. I'm writing all on top of myself. All right, so I have that. So we now have 3 out of our 6 zeros, and to get the remaining 3, we're going to work in this red part. So I need to know what values of x makes x to the third minus 3x squared minus 2x plus 6 equal 0. Well, we would have to try to use one of our solving techniques. And the solving technique that I'm going for, I have 4 terms to work with, is I'm going to try to group these terms, see if they have common factors. So I'm going to group the first 2 pairs together. So x to the third minus 3x squared. And then group the second 2 terms together. So it'd be plus negative 2x plus 6. And take out common factors. So when I take out the common factors of the first one, which would be x squared, I'd have x squared times, and what's remaining in there is going to be x minus 3. And then take out the common factor of negative 2 in the second set of pairs, and that's going to leave me with x minus 3. And I have that equals to 0. Now that I look at my line, I have a common factor of the 2 terms on the left-hand side of that expression of x minus 3. And when I pull the x minus 3 off, what I'm left with is x squared minus 2 is equal to 0. So I get a 0 here of x is equal to 3. So let me go add that to my list. So I got 3 as a 0, and the corresponding factor of that was x minus 3. And we just got one piece left to solve. We got to solve x squared minus 2 is equal to 0, which gives me x squared is equal to 2. Square root both sides. And the square root of x squared makes the absolute value of x is equal to square root of 2, which is gives me x equals positive or negative square root of 2. So my final 2 zeros, finally, are the positive and negative square root of 2, which was created by the factor of x squared minus 2. And so the factored form is just going to be all of these factors that we have times together. So factored form, let's see, x squared minus 2x plus 17. Times x minus 3 times x squared minus 2. There's my factored form. Now, let's do end behavior. So the end behavior, we do the leading term test. We go find the biggest exponent, which is x to the 6th. We look at its coefficient, which is positive 1. So we are positive coefficient, even degree, which according to our leading term test means that both left and right sides are going to go up. So we can describe the end behavior using limits. The limit as x approaches negative infinity for that function is going to equal positive infinity, and the limit as x approaches positive infinity for f of x is going to do the same thing. It's going to increase without bound.